Welcome to the second lecture of today, which will be given by Krishnendu. Over to you.
Okay. Maybe one can switch on the lights. Okay, so I'm going to first start with what we finished, what we talked about in the last lecture. So the first thing is that, so we talked a bit about this ETH, and then we decided that we are going to discuss two aspects of violation of ETH in systems. And one of the simple models that we looked into was this, XX model in a XY model in a magnetic field for spin 1. And we saw that there is a special class of states called the bimagnum states, which led to an emergent symmetry. And this emergent symmetry prevented dynamics within that sector, which has this symmetry, to be thermal, because they simply don't talk to the thermal states. Okay, so today we are going to talk about another model demonstrating this. And here, and part of the reason behind this is historical, because this was the first model in which this many-body scars came up. And part of the reason is that this is going to tell you one important feature, that scars in many-body systems may not be, may not have this exact symmetry. The symmetry may be approximate, and we are going to see what we mean. Okay. So before that, let me give you two references, which has very good discussion on the scars, and later what I'm going to discuss as Hilbert space fragmentations. So first one of them is by Barnavik. And this is Reports in Progress of Physics. That's the one. And the second one is an review article by Anusha Chandran, Shivaji Sandhi, Vedika Kemani, and Aidekola. And this came up in Annual Review of Condensed Matter. This is 23, I think. Okay. Both of these are on the archive, so you can also look at those versions. Okay. So these have some good description of. The first one is mostly about scars. The second one also talks a bit about Hilbert space fragmentation, and these review articles could be useful. Okay, so the system that I'm going to talk about is about these cold atom systems. Typically these are called Rydberg systems. So what happens is that there is a class of molecules, and where they have some ground state. So let me just write down the. So they have some ground states, which I'm typically going to call as G, and that has some atomic numbers. I think it's typically 5. Okay, I haven't charted it here, but most likely this was some 5s half and etc. So these are rubidium atoms. But these atoms also have something called a Rydberg excited state, which is very high up. It was something like 71 is again half and so on. Okay. Now the point, and then there is an intermediate level, which is important for our purpose. So what typically people do is to shine laser on this kind of atoms. So if they were initially on the ground state, so you can shine a laser, and through this intermediate state, you can excite them to a Rydberg atom. Okay. It's usually a two-step process. The first laser takes you somewhere here, and the second laser takes you somewhere there. Okay. And each of these lasers are detuned a little bit from the exact difference in of the atomic energies. Okay? So the frequencies of the lasers are such that they are not exactly in resonance with the atomic energy, they are a little bit detuned. Okay? And it turns out that if you look into this, the effective model that one can come up is a two-state model where you have a Rydberg state and a ground state, and they have a effective coupling of omega, which is like, so let me call this as omega r and this as omega blue, then goes as where delta is this detuning. Okay. So then if you think about it, if I had to construct a, and this, a lot of calculation goes into this, you know, there is this atom photon calculation where you have to sort of, you know, integrate out the atomic degrees of, the photonic degrees of freedom and get this effective thing. And this is all done in several papers. But the bottom line is that at the end of the day, there is a effective coupling omega between these, the ground and the Rydberg excited state. Okay. So once that happens, one can think of constructing a two-state model, because there are just two states on every given site, of a chain-like configuration. Okay. So on every site of this chain, there are two sites. So of course you can think of a coupling between the Rydberg and the excited state. And if I want to write it in the spin language, you know, because it's a two-state system, it's natural to think of a spin half. Then this coupling is just sigma x. Okay? Because it just couples the ground to the Rydberg excited state. So the Rydberg excited state is like a spin up, and the ground is like a spin down, and this is the coupling. And then there is another term which follows from the fact that these lasers are a bit detuned from the exact difference of energy between the ions. And this just tells you how easy or hard it is to excite an atom from the ground to the Rydberg state on a given site. Okay? So this is exactly like a chemical potential in some sense, you know, how hard it is to create an excitation. And so one gets a term like this, where n in the spin language would be 1 plus sigma jz by 2. It's just projected to the spin up. So that creates an excitation. Just measure the number of Rydberg excitations. How many of these atoms on the chain essentially is excited to the Rydberg state. But the real interesting thing about these Rydberg atoms is that once you have excited an atom, let's say here, to the Rydberg state, and you have excited some other atom out here, these states, because of some atomic properties, essentially experience a very strong van der Waals interaction. Okay? So basically there is a term which tells you that if there are two Rydberg excitations at sites I and j, they have a interaction which falls as 1 over r to the power 6, the distance between the sites. Now the thing is that there is some interesting ramification of this. So as you see that this interaction decays very rapidly as you increase the distance. Okay? But say this V is large, then at least for the neighboring sites, okay, if I have excited one Rydberg atom on a site given by, let's say, I, then on the site I plus 1, to excite that Rydberg atom, I have to pay an energy cost of V, you know, the additional energy cost. And if this V is very large, then the system is never going to produce two Rydberg excitation on neighboring sites. You know, it's simply energetically too costly, and the system doesn't want to do that. This phenomenon of blocking the second Rydberg excitation due to a Rydberg excitation which has already occurred in one given site is called Rydberg blockade. Okay? And, oops, I'm sorry. So, Rydberg blockade. Okay? So essentially what you are doing is you are basically, after you have made one Rydberg excitation, you are blocking this. And this blockade can happen at the neighboring sites, or if V is even stronger, it can happen at the second neighboring site, third neighboring site, whatever. And in an realistic experiment, most of it is done in Marcus Greiner's group at Harvard, they can actually tune this, the amplitude of V in an experiment, and they can go to regimes where this Rydberg blockade occurs over one site, two sites, three sites, and so on. The number of sites essentially defines what is called a blockade radius. Okay? So the typical blockade radius can be 1, 2, 3, n number of sites, depending on how strong the V naught is. Okay? So one regime which would be particularly of interest to us is the case where you have a Hamiltonian like that, and your Rydberg blockade radius is exactly 1. That is, if you create a Rydberg excitation on one given site, you are not going to be able to create a Rydberg excitation in the next site. Okay? Now, in this regime, imagine that this delta is large and positive. Okay? So the system, what it would do is essentially create as many Rydberg excitations as possible, subject to the constraint that there are no Rydberg excitations on neighboring sites. Okay? So then, on a given chain, it can create R, then ground, R, ground, configuration like this. And this R could be on either even or odd sublattice. You see, because I can construct this, but I could have also constructed this. Okay. These two are essentially. And now you see that in the language of spins, this is just like an nil state. And this is its partner, okay, time reverse partner. Typically in the literature, this is called as a Z2. This is called as a Z2 bar. Okay.
So large delta means high density?
No, large delta means that detuning out there,
Sorry.
that detuning is large and positive in some sense. Okay. So, or maybe large and negative depending on the sign that you use there. You know, in my definition, probably what I call as detuning there, it's minus delta, but I mean, that's, yeah.
No, what I'm asking is that this blockade, I would think, is probably more pronounced at high density, that there are many.
Yes. So the point is that here, there is, the density is fixed to 1 Rydberg atom per site. Okay. So whether that one atom per site, and whether that is on ground state or Rydberg excited state, that's different. But the density of Rydberg excitations, you know, how many you have, that is controlled by this blockade, large V. Yeah, you had a question.
Is it okay to ask a clarification on this excitations that you do in the Rydberg atoms?
What do you mean? Okay, what's the question?
So this omega excitation that you have, I understand that's a second order process.
Yes.
It's absorbing 2 photons and
That's right. It's a 2-photon process, sure.
Yes. So then what is this detuning with respect to what is this virtual state?
Oh, there is an intermediate atomic state out there, you know, whose details I have forgotten. But typically in their configuration, they first use one laser to excite from the ground to the intermediate, and the second laser to excite from the intermediate to the Rydberg. That's why it's a 2-photon process. There has to be 2 photons absorbed to go from one to the other.
It's an actual level, not a virtual level.
Oh, no, it's not a virtual level. It's an actual intermediary level, you know, which, yeah.
And this detuning takes you to the second order process. That's why.
No, the detuning doesn't. The second laser takes you to the second order. And you don't want to set the detuning to 0 in general, because then everything resonates, there are too much photon absorption, the system heats up, and all those kind of things happen. Okay? So that's not something you want to do. That's why you keep these detunings. Okay. Other questions? Okay. If not, let's move on. So what happens is that okay. Yeah. So now, using the fact that, you know, the only thing that this, so now I am in a regime where V naught is much, much larger than omega delta. But think of the potential energy that you need to pay for 2 Rydberg excitations which are neighboring, second nearest neighbor. that's V naught by 32, okay, 2 to the power 6, right? So that can still be small compared to these scales, okay? I can go into a scale regime like this. And if that's the case, then the only thing that the Rydberg excitation, this interaction does is to prevent Rydberg blockade on neighboring sites, okay? And that's pretty much it. Because this V naught by 32 term I can ignore, and I can get an effective theory using that. So in that regime, what one can do, 2 to the power 6. Because if two of them are separated by two sides, there is a 1 by 2 to the power 6 factor. Because the interaction goes as 1 over r to the power 6. Is that, yeah? Okay. So then, so then what happens in that regime, the only thing that I need is to ensure that my states, if I have a upspin, which is like a Rydberg excitation, I don't have a upspin on the neighboring sites. Okay, that's the only thing that I need to ensure when I think of my states. And that can be implemented by writing a local projection operator. Because if you look into that Hamiltonian, you see that the only thing that takes a downspin and convert it into a up is the sigma x term, right? That's the only thing that, so that has a sigma plus, which is going to convert down to up. Now, this process can only occur, an up can only occur if the neighboring two spins are down. That is, if the neighboring atoms are in the Rydberg state. And this is the key thing. So if I want to implement that, one thing I can do is to map this H effective to again an effective model where I'm just going to write this as and minus delta nj, etc., whatever, okay? So all I have done, and then I'm going to forget about my interaction. Because the interaction just prevented Rydberg excitation on neighboring sites, and this is what exactly it does. And this projection operator is simply 1 minus sigma jz by 2. It just projects to the down state. So it just tells you that this thing can act only if and only if the neighboring sites are down. Okay. So now if I am in the limit, in the regime where this delta is small, or I can neglect this model is typically called the PXP model. Okay. For obvious reasons, PXP. Okay. So, and it is in this model that people saw signatures of quantum scars. So I just wanted to introduce a model to begin with. Okay, so before I go further, is this model clear? How this is coming in the context of Rydberg excitation? Any questions on this? This one? So what is happening is that, see, the role of the interaction was to prevent Rydberg excitation on two neighboring sites, which means I cannot have a 2 up-up configuration, right? So then, since sigma x is the only thing that flips us down to a up, I need to ensure that once that happens, the neighboring two sides are down. So that I can implement by putting two projectors on two sides of it. And once I do this, I can completely forget about the interaction. And this is also typically this quantity. There are many ways of, some people call it xj tilde showing that these projection operators are there. Some people call it sigma jx tilde, again tilde showing that there are these projection operators there, and so on. This model in the literature is known as the PXP model, okay? And it's one of those models for which you can study these cars and stuff. Okay? Clear?
The delta is small in the
they can go to the delta equal to 0 limit. Okay? So, yeah. So, they can tune delta from negative to positive and all that. So this would be a PXP model in a magnetic field, so to speak, okay? Because it's 1 plus sigma z up to a constant, it's just a magnetic field, but you can tune up the magnetic field.
the energies of VR are greater than sigma, why is actually you take it?
This one? No, I want to work in this regime. I want in laboratory to tune such that this regime is there. And the reason I want to take it is I want to get into a state where I have this nil state as the ground state of the system. Okay. Of course, the nil state is the ground state of the system for large delta. It's not the ground state of the PXP model. Okay. So that I want to clarify. But I'm going to come to why I'm writing this in a moment. Any other questions? If not, let me move on. So apparently, the experimental observation that came out is that, so now imagine that I do something like a quench, in the sense that my model has this thing at some large delta, large positive delta, so that, you know, my ground state was this nil configuration. Okay. Then I suddenly turn off this delta to 0, and I want to see the dynamics. Okay. Now, when I turn off this delta to 0, this state, this nil state, which is a Fock state, it's not an eigenstate of this Hamiltonian anymore, and there would be non-trivial dynamics. And if you compute the average, so remember we computed something like psi naught h psi previously to see what the initial average energy is. And you would see that, you know, this initial energy puts it, this expectation kind of puts it in the middle of the spectrum. So you would expect that in such a dynamics, you would see ETH like thermalization. Okay. Because, you know, you are doing some quench, the system should give thermal behavior. So what you expect is a rapid thermalization, something like this. Okay. So for example, if you are computing any operator, say a spin-spin correlation operator or something, or expectation of sigma z, you know, any such operators, it will start from some initial value and then quickly go to its ETH predicted value, whatever that is, at some.
So why does Bench ensure that we are in the mid spectrum?
Oh, because this expectation value, this is close to 0. And so from there, you mean that it's in the mid spectrum. Okay. However, what you see, yeah. Nil state, yeah. So what you see instead is there are these oscillations which decay and it goes to some, and these oscillations are quite long time compared to what happens in this, compared to time scales that are given by the system. So if you make time scales out of the parameters of the Hamiltonian in your system, these oscillations are long-lived compared to those. This cannot be explained within the ambit of ETH. Okay, because this prediction, this is very different. But there is also this thing that these oscillations do not stay forever. You know, you have a first few oscillations and then they slowly die down. Okay. Now this phenomenon is somewhere in between what thermalization is predicts and what scar kind of dynamics gives. And the resolution to this is that, which I'm going to sort of show some pictures and stuff like that in a minute, is that these are examples of scars which has a finite matrix element in sense of overlap with the thermal band. Okay, typically we call them as leaky scars. You know, so the point is that what was protecting the scars in the previous model? It was this symmetry, right? This is emergent SU2 symmetry. Here, with this model, if you did an analysis like that, you would see that the symmetry is not exact. This SU2 commutation algebra is not closed. And that comes because of this projection operators. You know. There are many ways of seeing this. I'm going to sort of skip those because I really don't have time. But the point is that these kind of things essentially tells you that it's possible to have violation of ETH not only when there are perfect scars in the system, but also when there are approximate scars in the system. Okay, so there is this oscillatory period. So let me show you some plots and show how these scars come up. somebody need to, oops. Ooh. Can you switch on the projector, please? It's, ah. Doesn't look like it's. Ah, okay, good. No, but I can probably.
Just take and click once. Now you can.
Yeah, okay, good. Somehow it's cut off a little bit. There's something strange with this. Yeah. Can you just, yeah. Much better, thank you. Okay, so these are the scars in the PXP model. So what they did is that they took this PXP model, simply this P sigma x and P, and then they found out half chain entanglement entropy for all the states in the spectrum for a finite system. And there you see again this thermal band, okay? But you also see that there is this set of states, okay? And these are the states which contribute to the oscillations that one sees. And these states are the scars. They have low entanglement. So remember in the last class, we also saw something like this, where there was, for the spin XY model, there is this band of states which led to these scars. Here also, these scars are there. Okay? And also, if you see the overlap of the nil state with this, you see that this overlap is pretty high over this band, and these states are exactly the same as the states out here. So you see that there is an approximate because these oscillations die down, and you can understand why that is the case. But the point is that there are these band of states having high overlap with the nil state. That is, and this leads to these oscillations. And the oscillations occur because this is an order L number of states with almost equal frequency difference. So there is very clear oscillations that come in. However, if you would have done the same thing starting from the initial vacuum state, you would see that these states have almost zero overlap with vacuum. And there, if you just look into the similar, this expectation value of O, any operator, starting from the initial vacuum state, you would see clear thermalization. Okay? Therefore, this quantum scar-induced thermalization, is a weak violation of ergodicity, because it's only for some special class of initial state which has overlap with the states in the scarce sectors that shows this violation. Okay. Is that point clear?
What kind of entanglement scaling law these scars?
These are, it's hard to say. It's usually close to log L. Okay, but I'm not sure if it is, I'm not sure if it is exactly log L because it's not, so the analytical calculation is not there, but numerically it seems something similar to log. Okay. For the mid spectrum ones. Of course, if you are, the first state here is the nil state, close to the nil state actually. And that, no, sorry, somewhere in here is the nil state, and that, of course, oops. Okay, there is a password. Sorry. Okay, thank you. Yeah. So let me try to also now show something, and this is the last thing that I'm going to do about the scars part, where one can calculate in this model. So this OZ happens to be, this magnetization operator, summation over j sigma j z, and you compute this the variance of this OZ, and as we saw in the last class, this is related to this f square omega by this quantity. Okay, so the matrix element square is related to this f square, and normally this f or f square is supposed to be a smooth, slowly varying function. But here, of course, when you see this thing in the intermediate energy scales, you see this oscillatory behavior, and it turns out that the frequency of this oscillation exactly matches this energy difference. Okay, so from that, this was done in the group of Avanin and Papich and others. They concluded that these oscillations, this oscillatory behavior in f square, is a signature of this quantum scars. The other thing that happens, which is interesting, is that if you scale this mod f square at low frequency, and this delta now is the many body energy gap, which goes as 1 over d, that Hilbert space dimension. You see that so it plateaus to when you reach a very small energy scale. Okay, so apparently the plateau doesn't occur over a Thouless energy scale here. It occurs over a much lesser energy scale, and this is also one deviation from standard ETH like prediction. Okay, so whereas this kind of thing is a weak violation of ETH, f square, starting from of course this initial state which is the nil, essentially is going to show you some characteristic deviation from the standard ETH predicted f. Okay. So now yeah, maybe I can. So I'm going to switch over to the blackboard for the moment. Okay. So let me let's keep this, but let's just switch off the projector. Maybe. Okay. So this is all that I wanted to say about scar-induced violation of ETH. Okay. In the next part, we are going to see another violation of ETH which arises from Hilbert space, some phenomenon called Hilbert space fragmentation. Okay. So that's the last part of this lecture. So I'm going to sort of try to see if I can do this quickly. Okay. Yeah. The emergent symmetry is again approximate. It's an approximate SU2. So if you construct those operators analogous to J plus, J minus, and etc., that one can do. But you will see that the commutation relations doesn't actually close the SU2 algebra. It gives you something else. I mean, it closes the SU2 algebra and then there is something else. Okay. And as a result, that approximate SU2 is what is giving this emergent symmetry. Okay, any other questions on this? Okay, if not, let's go into this another phenomenon. So it turns out that in some constraint models, the statement is that so when we think of a many body Hamiltonian and just think of diagonalizing this, so what do? We take this Hamiltonian, we resolve all the symmetries, okay, which forms, so if I am in my Fock space, so these are going to form blocks, okay. So for example, if some charge is conserved, this is equal to q equal to n, q equal to n plus 1, and so on. Okay, so these are the symmetry sectors. Okay. Now this symmetry induced, and these symmetries, since the Hamiltonian commutes with this, states in dynamics in one symmetry sector doesn't talk to that in the other sector. So if you are in one symmetry sector, your dynamics is going to proceed to that. Now the point is that, however, if it's a generic global symmetry like conservation of charge or anything like that, there is usually order L, where L is the system size, number of such sectors. Okay. So for example, think of spin. If your total spin is conserved, it can take values from, let's say, plus L to minus L, and then you are going to have 2L. So order L number of such sectors. Okay. However, in some constant Hamiltonian, so in this sense, the Hilbert space is really fragmented into bits and parts, but this fragmentation in some sense is not that, its consequences are not that devastating, because within this you still have ergodicity and you can still do ETH and everything. Okay. However, in constant Hamiltonians, sometimes it so happens that even within a given symmetry sector, and this is very important, okay, after resolving all the global symmetries, and if I focus myself onto one of this symmetry sector, even within this, the system can fragment into an exponentially large number of fragments. The number of fragments which was OL for the symmetry thing, in this Hilbert space fragmentation thing, it goes as order exponential of L. Okay. That's the first statement. Okay. Once this happens, there is no hope to recover ETH, because ergodicity is really broken. Okay. And it's one of the strong violation of ergodicity. I'm of course going to give you a model and demonstrate how this happens, but let me first characterize the general features of this phenomenon, and then we are going to demonstrate it using a model. Okay. So the first thing is that there is exponential number of this dynamically disconnected sector in your computational basis. Okay. And of course, it's very important to state this, that it's in your computational basis, because in any many-body system, if you go to your eigenbasis, the states are always fragmented, right? One eigenstate doesn't talk to another under Hamiltonian evolution. But that's not what I'm talking about. That's trivial. That's not what I'm talking about. Even in the computational basis, this happens. Okay. That's number one. Number two is that if I now take so of course these fragments all have different dimensions. It can have many different dimensions. So suppose I take this fragment and I pick up the largest fragment out of this. It turns out that dimension of that fragment, so let me see, D of fragment, the largest fragment, divided by D of system, okay? And by D of system, I mean within the symmetry sector that I have resolved. This goes as exponential minus L. Okay. Now compare this with the scars. Okay. For the scars, what are the fragments? There are two. One of them is this symmetry sector, and the other one is this thermal sector that I had. But suppose I take the thermal sector and take the total system dimension. This would be of the order 1 in the limit of large L, because the number of states in the other sector is order L, and L by e to the power L goes to 0 in the thermodynamic limit. Okay. However, here, so for those kind of fragmentation, this goes to 1. However, here it goes to 0. Okay. And that's one of the key differences of this Hilbert space fragmentation with symmetry-induced dynamical sectors or scars, which are, for scars, of course, that's a weak violation of ergodicity. So, so people classify this into strong Hilbert space fragmentation where this happens, and weak Hilbert space fragmentation where the other things happen. Okay, that's one way of classifying this phenomenon. Okay, that's the second point. Sorry, yeah, okay. The third point about this phenomenon is that, okay, let me see what I wanted to say. Usually in Hamiltonians, which shows this Hilbert space fragmentation, has at least two global conserved quantities. One charge, another like a dipole moment, things like that. Okay. So 2 global concept. Okay. So typically this is some charge and dipole moments, but and also this varies. So the exact nature of this concept quantities varies from model to model, depends on the model you have taken. I'm going to try to show you at least 2. So let's see how that goes. So number 4. Yeah.
So the number of this symmetry centers, that is n.
That's right.
I go into
Order L.
Order L.
Yeah.
And I go into one of them.
Yes. So you have resolved all your symmetry. You have gone into one of these sectors. Within that sector, you see dynamically disconnected exponentially large number of fragments. That's Hilbert space fragmentation for you. Yeah.
Sir, after resolving all the symmetries and when I have gone into a particular symmetry sector, there I see some fragmentation, but the number of such fragments still remains polynomial, not exponential.
Well,
Then will that also be called
no, not strong Hilbert space. You can have a weak Hilbert space, like the scar, this thing.
then that will be called
Weak, not strong. Okay. So this ratio, this is an interesting thing. This ratio either goes to 0 exponentially or it goes to a constant. It would be interesting to find a model where there can be a polynomial change to 0. I mean, if it goes to 0 polynomially. I don't know of a model where that happens.
model where number of fragmentation is polynomial, but it is
No, not number of fragmentation. The dimension of the largest fragment divided by the dimension of the system. If it goes to 0, of course, it's strong Hilbert space fragmentation. But how does it go to 0? Usually, all the models that I know of, it goes to 0 exponentially. So it would be, what I'm saying is that it would be interesting to see a model where it could go to 0 polynomially, because that thing is not sort of ruled out by this phenomenon. Okay.
Sir, so this Hilbert space fragmentation happens in some bases, right?
Your computational basis, whatever you want to say. Typically, people take this this thing. Okay.
Like if the initial state is made up of some components in different fragments.
Then the dynamics will be very different, because you are going to see different dynamics from each of these components, and they are not going to talk to each other, and there are ramifications of that. I'm going to come to that in a moment. Okay, so another thing which happens in most of this, again, this is not a necessity, but it happens in most of the model, is that there is a large number of Fock states in this, which are zero energy eigenstates of the Hamiltonian. I mean, the Hamiltonian just annihilates them. So, and these states essentially, when this fragmentation happens, there is usually an exponentially large number of these states. This is a size 1 fragment, if you will. Okay. Okay. So two things, so when such a thing happens, there are two aspects which are interesting and can be tested numerically. One of them is that, you see, in this case, the dynamics is such that the system retains a memory of the initial state. Because, it's pretty obvious, because if you pick up a state at random, its dynamics is going to proceed only by the states within the fragment to which it belongs, because it dynamically doesn't talk to others, this thing. As a result, it will retain that memory throughout the dynamic. So what happens here is that the autocorrelation function of an operator starting from an initial state, of course, this is a connected autocorrelator, okay? Started from the initial state, doesn't vanish at long times. It goes to a bound which essentially goes as 1 over L to the power some power in one-dimensional systems. This bound is known as, typically called in the literature as Mazur bound. Okay, that the autocorrelation essentially goes to a finite value. It cannot go below that. Okay. That's one aspect. The second aspect is that one very interesting numerical experiment. You pick up a state at random from your fragmented this thing. Okay. Now, if there is no fragmentation, you pick up that state, evolve it with Hamiltonian and compute its entropy, entanglement entropy, half-chain entanglement entropy, as a function of time. Okay. Typically, you would see that if there is no fragmentation, all those states will go and saturate to a value which is known as the page value of that sector. And it roughly speaking, it would go to as log d, which is the dimension of the Hilbert space of that symmetry resolved sector. Okay. This is of course very approximate. The exact values of this S page, that is the page value of this thing where it saturates, that depends on various details and can be calculated. Okay, but roughly speaking, it depends on the log of this Hilbert space dimension. Now the point, interestingly, think of what would happen if you had a situation where you are picking up these states in random, but in a Hilbert space fragmented setting. Okay, if you did pick up a frozen state, it will just stay, because it's a Fock state, its entanglement entropy was 0, and it will just simply stay to be 0, because the states are frozen. They don't, it's a one-dimensional Hilbert space. There is nothing to evolve, right? It's an eigenstate. It will just simply go to 0. You pick up some other state. Maybe it's a sector, it's a state with some dimension, let's say, some n naught. Then this will go to log n naught and not log d. So different states out here will just go to different values of this page value. So pick up all random states, they are going to go to different values. Okay? And this essentially tells you that your system is fragmented. Because when you pick up a state in random, it knows which fragment you have picked it up from, and then its value saturates to the largest, to the Hilbert space, to the page value of that fragment. Okay? And this matters because SP, so this matters because, this matters because you see that SP by SP of fragment, okay, is log d, roughly speaking, is log d of the fragment. And we have already seen that the largest fragment, is exponentially small compared to, the Hilbert space dimension is exponentially small. Therefore, this is a finite order 1 number less than 1. And you can actually see what that number is. So for example, for the largest sector, this may be something close to 0.7, 0.8, but less than 1. Okay, and that can be picked up. Okay. So now with this in mind, let me go to certain models and try to see, what kind of constant models can give rise to this kind of Hilbert space fragmentation. Okay. So, Shumik, I started a bit late, so can I take 5 or 10 minutes extra, if necessary? I don't really know, but yeah, thanks. So, yeah. So, the first model that I'm going to talk about, this was also one of the first models that was used to show Hilbert space fragmentation. It was done by, I think, Pablo Sala and then Frank Polman and that group. Okay, but the model is something like this. Okay, so it's a spin model, spin 1 again. Okay, but the model has a very peculiar Hamiltonian. Okay. Okay. So basically, this changes the spin from whatever. So the three states again are minus, 0 and plus. These are the three eigenstate of Sz because it's a spin 1 model. So this model takes minus to 0 and 0 to plus and so on. Okay, this operator, and this one takes plus to 0 and 0 to minus and so on. Okay. Now it turns out that this is an example of a model with a Hilbert space fragmentation. My question is why? So to understand that, the simplest thing is to check things by a collection of eigenstates. So for example, if I take a state psi naught, Fock state, which is all zeros, okay, at different sites. And you see clearly this is annihilated by this model, because whatever side this Sj minus square is going to go, it's going to annihilate this. Okay. So this is an example of a frozen state. Under the action of this model, this state is not going to go anywhere. However, this is of course not enough. There could be a few states like this. But then you realize that it's much more, in the sense that if you consider a state j plus 1, where you have all zeros, but then there is either this j plus 1 or two minuses j plus 1. So you can think of this as something like this. Okay. You either have two pluses or two minuses at consecutive side, flanked by all zeros. Okay. Now you can see that any two individual consecutive pluses and minuses are also going to be annihilated by this model. Okay. This is kind of easy to see because, the point is that if you have two individual pluses, okay, out here, then if this S minus can act on this to give you a minus, but the point is that the neighboring thing has a plus always, and that's going to annihilate the stuff. And you can work on this with this thing. The Hermitian conjugate stuff is going to sort of also do something similar. Okay. But now you see that you can place this j plus square in your Hilbert space anywhere. Okay. So that already gives you an exponentially large number of states which are frozen. Okay. So those are the frozen states for you. Okay. So the point is that there is one way to count how this can happen. So let me see if I. Yeah, so there is a small way to estimate how the number of this frozen state okay, I think I can. So maybe I should do it here. It's probably better. So let's try to estimate this number of frozen states. Okay. So since this is a three-state model, there are three sites involved in each term of this Hamiltonian. So I can take three of these sites, okay, neighboring sites, and let's say I arrange them in a triangle, okay, just for the sake of. So I map this onto a triangle with three sides. Okay. Now the point is that if any of the two neighboring sites has a plus or a minus, okay, or of all of them are 0, then you have the frozen states. Now clearly these three sites are 27 total number of spin possibilities, right? Because 3 to the power 3. And it turns out that you can do this counting that 19 of them are frozen. Okay? But in a chain of length L, and this counting you can do. You can place these pluses and minuses, etc., and just see, how many of these corresponds to this frozen site. So the frozen state corresponds to two pluses or two minuses on neighboring side, which essentially means that there has to be two pluses or two minuses on any of these, or all zeros for that matter. Okay? So the counting can be done. Now the point is that how many such triangles can you make out of a chain? Now you need these three sides, okay? So you make one triangle. If there are four sides, you can make two, one and then two, okay? And then 3 and 4 and etc. Of course, these are not independent, But for the sake of just a rough counting, I'm going to sacrifice that. And then you see you can totally make n minus 2 of these triangles. Okay? And then the total number of states is of course this fraction times 3 to the power n, which is the total number of states in U. Okay? And this turns out to be 2 point some number. Okay, I'm not entirely sure, but yeah, goes as something like this. Okay, this counting has been done in the literature in various contexts. But the point is that this is just to show that this kind of states gives rise to an exponentially large number of sectors. Okay. And there are many other states. So one example that I'm going to give you, and just to show that these zero energy states are not the only fragments, there are some other fragments which one can sort of look into. So for example, you can have a state like this. Okay? So start with all the pluses, but then do a 0 plus 0, and then again do all the pluses. Okay? Think of a state like this. And then think of another state where you have this plus, 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 etc. And then you have a plus, minus, plus, and then all the pluses. Okay. These two states essentially map onto one another under the action of H. Because you can clearly see that if you take the first term of H out there, and if this is your J plus 1, for example, this is going to give it minus, and these two are going to be plus. Okay? And that's the only state, because all others are neighboring pluses or minuses, they cannot move. Okay? So this is an example of a size 2 sector of your Hilbert space. Okay? So essentially, and there are many more, okay? So things like that, you can keep constructing. So the point is that these kind of things already tells you that, and when you try to look into this numerically, you can identify the largest sector and you can compute the sector where you have, you can compute the Hilbert space dimension of that sector and try to find out whether it's, how it scales with 3 to the power n, and you would see that it's exponentially small. Okay. So this has been worked out numerically in details in this paper by Pablo Sala and others. And this was the first model where Hilbert space fragmentation came up. Okay. So to demonstrate these other properties, I'm going to sort of move into a somewhat simpler model, which is also interesting, a model involving fermions, where again these kind of things happen. But there, the easy part of it is that there are some analytical calculations that one can do to estimate the number of the sectors, which I wanted to show. Okay, so let me just move on to that model. So any questions regarding this? So I just tried to demonstrate that a model like this, has this this exponentially large number of zero energy sectors, and also other sectors of size 2, and there are many more. Okay. Now one thing that before I leave is what are the conserved quantities in this model, because I said that there are 2 global conserved quantities. One of them is clearly the charge. Okay, it doesn't change the total charge, because you see that it changes 2 to plus and then 2 to minus. So Sz, which is summation over J is Jz, that's certainly conserved. The other thing which is conserved, which is a bit more difficult to see, is the dipole moment dj, which goes as J times Sjz. Okay. And so the point is that here there is an ambiguity, because once you define a dipole moment, there has to be an origin that you need to specify. And I have taken this definition works when you take that origin J0 to be 0, and the number of chain length is odd, in the sense that you can have minus J to plus J through 0. Okay. So these two, the dipole moment corresponding to Sz and the total charge, these two are conserved. Now, to see, for example, why this dipole moment is conserved, it requires a bit of thought, and I can show this by some neighboring these things. Okay. So, for example, let me just tell you what this dipole moment is. So, for example, if you had a configuration like plus minus, okay, then you see that this has Sz equal to 0. That's easy because plus and minus. But its dipole moment is minus 1 if the plus is to the left, and if you had a configuration minus 1, it's equal to plus 1 if it's to the right. Okay. And then you can think of what the Hamiltonian does once it acts on this and try to find out what the dipole moment of that state is, and you will see that this Hamiltonian commutes with the dipole moment operator. Okay. So it's a two-line algebra, but I need to move on in the interest of time, so I'm going to leave this here. Okay. So any questions about this model? Then otherwise I'm going to go to the next and do some counting there.
So,
yeah.
If you look at the given defined as fragments, do the states follow some special type of, they have group structure?
No, it's not a group structure. There is no groups, at least not to my knowledge. But any state, any Fock state that you pick up is going to belong to a fragment, and that's pretty much it. If it's a frozen state, it's not going to evolve. If it's non-frozen, it's going to evolve, but not thermalize. Not thermalize in the original ETH sense of the entire Hilbert space. Okay. That's the only thing that I know. I mean, I don't think there is any group structure or symmetry associated with it, because this is not something which is induced by symmetry. Having said that, I will say something that I didn't want to bring in, but let me just say it anyway. So, when you do this MBL, this many body localization thing, their states are localized, and so there is a conserved quantity called tau, this localized integral of motion, people typically call them. So these tau essentially this is not a physical operator, okay? But tau at any, but if you can construct this tau as a sum of physical operators, in given sites, it turns out that these only has weight on a specific site, okay? And that's where the localization comes from. In this kind of thing, Hilbert space fragmentation, so this, again, the Frank Polman's group, they came up with some quantity which is not exactly a conserved charge in this sense, like the taus are, not a localized integral of motion. What they came up is they call it statistically localized integrals of motion, meaning that if you construct operators like this, okay, then its expectation on a typical state, okay, is going to be localized in some spatial region. And that's why this, so that essentially characterizes this kind of fragmentation. But that's the only characterization that I know of, okay? Not some symmetry or this thing. Okay? Okay, so let me just move on to the next model, and that would be the last thing that we are going to discuss in this. This model is a fermionic model which hops on the lattice, okay? Which is, whose Hamiltonian, again, is given by some J with some constant, which is just some energy scale that I don't care so much about, times some projector, Pj, and then a hopping Cj plus 1 Cj, and then again the same projector plus its Hermitian conjugate. Fine. This projector essentially has a funny character. This projector is given by 1 minus nj plus 2 minus nj plus j minus 1. whole square. Okay. So let me try to tell you what this means. Okay. Since I have defined the model. So now think of a bunch of fermions on a given site. Okay. So let's say there are these a bunch of fermions out here. Okay. Now the closed circles are the particles and the open circles are empty spaces or holes. Okay. Now if this one wants to move to the next space, okay, what this thing is saying is that this can only happen if the occupation of the J plus, so let me, the occupation of the J plus 2 site and the occupation of the J minus 1 site are the same. Okay? Which essentially means that in this setting, this fermion can never hop. Okay? Now, what does this physically mean? Why do I need this? What is it conserving? Well, you see, the point is that here, if I look into this, the number of bonds, these bonds, which has both occupied at both ends is 0, right, in this configuration. You see, this doesn't, this also doesn't, and there are no such, and only one, sorry, this is the only one, okay. Here, this is the bond where both the sides are occupied, okay. If this hopping were to take place, this number would increase to 2, okay. And these projection operators essentially tells you that I am going to allow hopping only when you do not change the number of bonds whose ends are filled. Now, how can such a model come in? It can come in if you have a very strong term nj plus 1, right? Because then this just counts the number of bonds whose ends are filled, right? And therefore, if you don't want to change this by hopping, because it will take a huge energy cost or it will lead to a very lowering of energy in some sense, then you are going to have a model like this. Okay? So indeed, this was done by Ardacola's group. They showed that the large V model of an hopping Hamiltonian in interacting fermions, the large V limit of this is essentially this effective model. Okay? So you take a bunch of fermions, allow them to hop on a lattice, and then just put a very strong nearest neighbor interaction. You are going to see effective dynamics of this constant model. Okay. The number of bonds are not going to change.
Why do you need two projectors here? I mean, one projector ensuring that the J minus 1 and J plus 2 has to be identical.
Yeah, but you need to, so the state first need to, you don't need to. I mean, you can do this with one projector, but it's the same. So what is conserved here? So there are two quantities which is conserved. One is the total number of fermions, okay, because this doesn't change the total number. So n, which is summation over j nj, is a conserved quantity. But the other conserved quantity is nb, the number of bonds with both the sides occupied. Okay. So these two are the global conserved quantities that one has. Okay. And in addition, there are some other conservations, but those are not that important. These two are the ones which are important for getting this fragmentation. Now the question is, how do we know that this is fragment? First of all, as you can see, let me just again draw this thing, and then I'm going to sort of do some algebra. So one of the states that one knows is completely localized, a frozen state, is a state like this. So you just take and keep repeating. Okay. And here you see, no matter what, none of this can hop. Okay. This is an example of a frozen state. Okay, it's one example. And then, sorry, and then you also have examples of other states. So I'm just going to, so think of a state like this. Think of an initial state like this, okay? Now, you see here that for this fermion out here, it can hop to the left. Okay? That is all right, but it can hop. So, for example, the action of the Hamiltonian can take you to a situation where there is this. And then another action, for example, could take you to a state. Now that you have done this, then you see that this particular fermion can hop because it's 2 to the right and 1 to the left, both are occupied. Okay? So you can have a state which is like and so on. Okay? So this is an order L sector where hopping between these different states are allowed. Okay.
Sir,
Yeah.
can you again tell how this hopping happens in this Hamiltonian?
The hopping goes from one side to the next, provided. So here is a side j. Okay. So this fermion can go to the side j plus 1, provided the occupation of j plus 2 and j minus 1 are the same. Okay. So it's a 4-site thing, and you need to figure out whether the hopping can happen by looking at the occupation of the j plus 2 and j minus 1. And what it ensures is that once you hop, the number of bonds with both occupied sides, that number doesn't change. See, for example, here the number of, so here if this j minus 1 is empty, okay, then the number of bonds here is 0, right, between these two. I mean, it's not occupied. However, if it hops here, it gets an additional bond where both sides are occupied at the end. Therefore, this hopping cannot take place. However, if this was occupied, for example, then this hopping could have taken place because because if this was occupied, for example, then there is this one bond here and there was this one bond here, and after the hopping, if it goes out to here, then there is one bond here and one bond there. So the number of bonds don't change. Okay. So those are the only processes that are allowed. Make sense? Okay. Good. Okay. So now I'm going to go to the laptop actually. So can somebody? Yeah.
Do you always need these kind of two concept quantities to have fragmentation?
In most of the models that has been studied, this was there. I know of at least one model where this was not the case, but that's sort of rather an exception than the rule. In most cases, this is there. No, it's not necessary. I mean,
the quantity that will be concept, that is also not the same quantity.
no, that depends from model to model. What do you call as dipole and what do you call as charge, that of course depends on.
What if they were more than the quantity?
Probably there would be even stronger fragmentation, but I don't know. But this is the minimum that is required actually. Okay. Such.
So here we have some exact formulas for the sector stability.
You mean in this model? Yeah, that's what I'm going to show. Okay. Just in the interest of time, I'm going to do this over the. Yeah. Okay, so now for the rest, I'll just use the transparency so that's easier in some sense. So here is the model that I looked into, okay? And here is this number of bond conserving projection operator, okay? The point here is that, so for the sake of it, let me just also define this. So if you have two sets of fermions which are next to each other, this is typically this kind of thing. This is typically called a particle defect. That's just a terminology, okay? And if you have two sets of holes, it's called a hole defect. And this is the sector that I showed you. The number of particles and defects are always separately conserved. Okay. The conservation of number of defect is just the statement of conservation of number of bonds with occupation on the neighboring ends. Okay. So how do we know that this is fragmented? For this, so we need to do some counting. So first, what we need to do is that we need to identify the largest symmetry sector. So if, in this case, if I have L sites, okay, then the number of particles being L by 2 is the largest symmetry sector. And and this also has, so since the number of bonds are also conserved by this Hamiltonian, the number of bonds are set to L by 4. So it turns out that this happens to be the largest symmetry sector of the theory. So how many states are there? So how do we count this? So to do this, let me first fill L by 2 sites with particles keeping L by 2 bonds. So for L equal to 8, I have 4 particles and this is how I do this. So now you see I have put in all my particles, however my bond number is not right because now I have 1, 2, 3, 4 which is L by 2 bonds. Okay. Next, what we need to do is to sort of insert the empty spaces or the holes such that I can break L by 4 of these bonds, because then I'll have the remaining L by 4 which is the correct number that I need, and this can be done in L by 2 C, L by 4 ways, okay, because I need to break 2 out of this 4 band, it's a 4C2 kind of thing, so, okay, so that is easy to see. And next, what I need to do is that I don't have, since I have L by 2 particles, I must have L by 2 holes, but here I only have L by 4 holes right now. So I need to insert 2 more holes, or rather L by 4 more empty sites in such a way that I don't break any more bonds, because I already have L by 4 bonds. Now this is a classic partition problem, which is saying that if you have n number of spaces and you need to insert n number of particles in those spaces, what happens? The answer to this is L by 2 minus 1 C L by 4. Okay. And when you, so therefore the total number is the product of these two. And of course, you are talking about particles and holes, but there is always, you can switch particles to holes and holes to particles, and that gives you a factor of 2. And therefore this quantity goes as 2 to the power L by L. That's the dimension of the largest symmetry resolved sector with charge, with L by 2 particles and holes, that is total charge is 0 or L by 2 depending on how you count it, and L by 4 bonds. Okay, that's the thing. Gosh, what happened? Sorry, yeah, okay, thanks. Now, here I need to count the number of dimension of the largest fragment. Okay, and this is the most tricky computation. So let me just try to see if I can get it right. So the dimension, so it turns out that the dimension of the largest fragment is the one where there are, of course, there are L by 4 bonds, but there are L by 4 particles and hole defects. That is, there are this adjacent L by 4 particles like this, okay, and these are the particle defects, these are the hole defects, and whatever remaining is there, is particle hole pair. So for example, if I have L equal to 12, for example here, then L by 4 particle defects essentially means that I have 3 particle defects, which is 4 particles placed next to each other. 2 of them forms a defect, then the other 2 forms another, and the third one. Then there are 4 of these holes giving me L by 4 particle defects, and then the rest are particle hole pairs. Okay, and this is one of the possible initial configuration, one of the states. Okay. Now to count the number of the states in this sector, the strategy is to start from this state, which is a simple Fock state, and see how many, what happens when I apply the Hamiltonian here. What hops and what are the states does it go to? Now you clearly see that these particles and holes out here are frozen, but the particle hole pairs are not. So for example, this pair out here, this up and down can go to this down and up. This thing can hop. As a result, you can see that the hopping process here is like a diffusion process where these particle hole pairs go and puts themselves within the space of these particles, particle defects or the hole defects. And since there are 2nd minus 1 such spaces, okay, for nd of particle and hole pairs, then of course, so there is total nd particles and nd holes, and therefore there are 2nd minus 1 spaces between them. Yeah. 2nd minus 1 spaces between them. Okay. So then this problem goes to counting of p balls that can be distributed between 2nd minus 1 bars, okay, because there are p particle hole pairs. This is this classic bar and ball problem if you have come across this. And that number is known. This is given by this combination, and therefore you can compute this. And now you see that there is a factor of L by which you should multiply because you started from this state. But nothing told you that the particle defects should start from a state j equal to 1. It could have started here, there, etc. So there are L such combinations. And L by 2 such combinations because it's periodic, it can go up to here and then it will repeat. Okay? So therefore you multiply this. And when you do this computation and you see that nt by n1 which we computed, it turns out to be a number which is like 0.8 to the power L, which means exponential reduction, which means that the dimension of the largest fragment is exponentially small compared to the dimension of the total sector, symmetry sector. So this tells you that as I go to the thermodynamic limit, this thing is going to go to 0 exponentially, and this is an example of a strong Hilbert space fragmentation. Okay? So in this model, this counting is analytically possible and it's easy. And so now I'm going to show you some plots on this model. So forget about this particular thing. This is an example where I'm looking at this model without the projection. Okay? So I picked up largest states from Hilbert space, etc. Forget about these numbers, doesn't mean much. But all of this essentially goes to the page value. Okay? But here, when I pick up random states out of this, in the fragmented model, it goes to different values depending on the sector from which you are choosing it. Okay? And also this autocorrelation function, the brown one is an example of a case where the fragmentation is not there. And the green one is an example where the fragmentation is there. Again, never mind what this is. So you clearly see the difference between in the correlation function, in the long time behavior of the autocorrelation function. Okay? And numerically, one can verify this analytical calculation. It's not an exact match, but it essentially goes to some number to the power L. Okay, in this model. So once this kind of Hilbert space fragmentation takes place, ETH is bound to fail. Because one of the key thing about ETH is about loss of memory. You start from an initial state, you evolve for long enough, you are not going to have any information about the initial state, or in other words, any information that was in the initial state cannot be obtained by any local measurement that you make. Of course, if you could make a complete global measurement and n number of them, and then you are going to retrieve that information one way or the other, but it's not very easy or not even possible in standard experiments. However, in any of this where the memory of the initial state is retained due to this fragmentation, ETH doesn't work. Okay, and these are the signatures which are the violation. This brown curve, for example, is what ETH would tell you about the correlation function. The green one is what this fragmented structure would give. And this tells you the difference between the entanglement. Okay, so these two, the weak fragmentation, and that is due to the weak fragmentation or scarring, that's a weak violation of ETH, because if you pick up states at random, for most of the states you are going to see ETH, and only an order L states which has overlap with the scarce subspace is going to give you ETH violation. But this is a strong violation, because if you pick up states from random, more often than not, well, for almost all the states, you are going to see a completely different behavior than what ETH predicts. Okay. So I think I'm going to stop here. And so to conclude, I mean, this ETH is our way of understanding how dynamics and correlation happens in a closed quantum system. And that's that's sort of like the norm. Okay. So it's like gambling. The house always wins. ETH always wins, except for these few special cases where you can be the winner, by violating ETH. I think I'm going to stop here, and thank you for your attention. Yeah.
So, what is the difference between integrable system and this strong reverse space and scarce kind of phenomenon? What is the difference?
So in integrable systems, what happens is that there is this large number of conserved quantities, right? So there are these conserved charges. So you can write down these charge operators, and you can. However, here you cannot. So there is no conserved operator as such, but as I said, there is this statistically localized integrals of motion, meaning that you can construct operators, at least in simple models, whose expectation in a typical state is going to be localized. And typical state is important, not in all states. It's not guaranteed. So that's one difference, and the number of sectors I think is also quite different actually. Yeah.
So the model that you said about the Pavlov's model.
The spin model.
The spin model.
Yeah.
The spin one.
Yeah.
So they called this plus or minus as the factorial charges over the C of 0.
Yes.
And the hopping of this factorial
Is like that your dipoles can move but not individual this thing. Yeah, sure.
Some kind of So is it analogous in this Fermi model that the hopping is similar? The Fermi hopping is similar?
No. So here you don't have an analog with factor in a very easy way. In Pavlov's, the spin one model there is a direct analog, but here it's not, because you see the point is that all you are doing is to conserve the number of bonds. Okay. This doesn't mean that a particle. So it's not always that a particle pair is moving. It's not like a dipole that is moving along. So that thing is not there. But of course the thing I think in both cases is that there is some higher form symmetries which is conserved, in the sense that dipole symmetry out here and stuff like that. That analog is there. Okay. Yeah.
Here in the quantum scar case, you have just showed that the new state has this high overlap with the, but in other kind of models it will be like different states will have.
Yes, absolutely.
Is there a formal way to know that which kind of
Well, in the models where you can see this scarce subspace analytically, then there is a way to know. Right. For example, in the AKLT model or in this Hubbard model or the spin one that I talked about, there people know at least some of the states. But if it's a numerical thing out here, this I don't know how to. Otherwise, unless you do the numerics, there is no way of.
Any more questions? If not, then
Yeah, sure.
Integrable system, if we do the statistics, we get the Wigner-Dyson distributions.
No, Poisson.
Poisson distribution. So for the scarce and inverse compatibility.
No, okay. So let me. That's a very good question. Thank you. So I should have said this. I missed it. So for the Hilbert space fragmentation, typically the largest sector that you have has a large dimension, at least in the large L limit. 0.8 to the power. So it's still quite a large number, and you can do the statistics. So for most of the cases, for most of the models that I know of, except for one or two, these sectors are ergodic. So they are going to go with Wigner-Dyson, but with parameters of the fragment, not of the entire Hilbert space. Okay. However, there can be models where these largest sectors can be integrable. So it can be both ways. And of course, when it goes to smaller sectors or frozen states, which is dimension 1 subspace, then of course you don't do statistics with that, right? That question doesn't arise. Yeah. Okay.
Okay. Any more questions? Okay, so if not, then this brings us to the series of lectures given by Krishnendu, and let us thank him for this lecture series.